Here, in the left member of the equation, we will collect the cross correlations of x and y for the different time differences. On the other side of the equation, we'll have a scalar constant, Ts, and then this summation can be written as the product of a matrix and a vector. The vector will have the values of the impulse response, which we want to determine. So, k goes from 0 to n minus 1. These are the same time values that we have here. As to this matrix here, it will collect the values of the autocorrelation of the input x. Here, in the first equation, g of 0 multiplies our x of 0. G of ts multiplies our x of ts, and so on and so forth. In the second equation, when this is 0, here we will have g of ts, because when this is equal to ts, here we will have ts minus ts, which is 0. So it is here that I will have Rx of 0. So here I will have Rx of ts, and of course, when this is 0, I will have Rx of minus ts. Of course, we know that the autocorrelation is even. So this matrix here, which as you may see is the matrix of the autocorrelation values, will be symmetric. Let this vector be Rxy. Here we have a scalar. Here we will have this matrix Rx, and here a vector G. We can determine G using the inverse of this matrix here, multiplying this vector here. Of course, this can only be written if this matrix is square. Let us now think about the dimensions that these vectors and matrix can have. We know that we have n plus 1 points here in G. However, we know that if we use n plus 1 points here, we will have to calculate the values of the autocorrelation until that same size. This will be an n plus 1 times n plus 1 matrix. But we know that such values will be poor estimates. So in fact, other than this scalar here, we should have a matrix with less columns and less lines. We will only find values for G here, but only here will we have good estimates. So it is better to neglect this and only use this part of the equation. Of course, if this submatrix is square, we can still write here an inverse. On the other hand, if we use less lines than columns, we will have an overdetermined system, which may provide us with less points for the impulse response, but with a better estimate. In this case, of course, we'll have to resort to the pseudo-inverse. In the case in which we use a certain number of columns here, certainly less than n plus 1. Remember that it is often reasonable to restrict ourselves to only about half or even 1/3 of this number when calculating autocorrelations and cross-correlations. And then we will restrict further the number of lines so as to have an overdetermined system to obtain the advantages of an overdetermined system, including, namely, some noise elimination. So the sizes of these vectors and matrices will be once we find the impulse response in this way, then what? Well, then there are two things we can do. First, we can use the impulse response that we have just found to find a model discrete in time by fitting the response of the model with the structure we offer to the impulse response, or we may numerically find the Fourier transform of this impulse response and thus find the frequency response of the plant. Plot the Bode diagram, and from the Bode diagram identify a model. In this case, a model continuous in time. From the asymptotes of this frequency response, or using the Levi method,